Intel analyzers include several different tools, but I'm going to talk about the VTune, Advisor, and APS. So it's kind of confusing because if you're familiar with NVIDIA tool set, they just have the two types of tools, right? Basically, it's three, but the graphics tool is not used by the HPC community. So basically, NVIDIA users are using NVIDIA Inside System and NVIDIA Inside Compute, right? So what they say is if you want to run the lightweight analysis, NVIDIA system will provide the host and GPU activity with the minimum overhead. And if you want to have a lot of detailed data for specific kernel, they recommend to use Inside Compute, right? So which is good. But Intel side is a little bit more complicated because Intel has a longer history than NVIDIA for the HPC community. Believe it or not, they had a lot of legacy part from the CPU side. So while they are developing Aurora, they extended some related features from CPU to the GPU. They extended them. So it is why the structure is a little bit more complicated than the other vendors, but what I can say is you will be able to find out some equivalent feature if you're expecting on Intel side, but it's a little bit complicated. Okay, so Rupak Roy has prepared this material mainly, and I just have them help him out, but he unfortunately cannot be here, so I would like to present it instead of him. So the agenda is we are going to talk about some overview of VTune Profiler and then some features of VTune Profiler, and then we'll talk about the advisor. You don't see the APS, right? Because APS is part of the VTune. It's confusing, but anyway. So VTune Profiler. So VTune Profiler is the basic the performance profiling tools for Intel products. So it is a suite of profiling for CPU, GPU, NPU, memory, cache, storage, offload, power. Yeah, we can say everything. And it support the SQL, C, C++, Fortran, Python, Java, etc. And the Linux, Windows, and more, some virtual machine as well. So it collects the hardware, software sampling data, tracing without the recompilation for the kernel level analysis. And then also it can provide some result on your source and the architecture diagram, histogram, and timeline. So it has nice GUI interface and it has a lot of different features. So you can be lost when you start something from random place. But anyway, which is great tool and a lot of features. So this is kind of some overview diagram, what kind of feature you can use for this kind of approach. So if you are interested in algorithmic optimization, hotspot analysis on anomaly detection and memory consumption analysis is recommended. And microarchitecture, memory bottleneck, you can use microarchitecture exploration and memory access, but both of them are pretty on the CPU side. And if you're interested in accelerator XPU, including GPU, GPU offload analysis and GPU compute hotspot analysis are recommended. And then for parallelism, threading, and HPC performance analysis is recommended. And also for platform-based analysis and multi-node analysis. So for multi-node analysis, they recommend to use APS, application performance snapshot. So from these features, if you are working on the Aurora GPU part, you can just remember, okay, if you want to run something in the multi-node, 100 node, 1,000 node, so we recently tested it with the quarter of the Aurora system, which is a 2,560 node. APS is working pretty good, so you can use APS. Don't try VTune for the 10 many number of nodes. It will take forever. And if you are interested in the device level optimization and node level optimization, you can try some GPU hotspot analysis, which include a lot of the hardware counter data, or GPU offload analysis. It provides some GPU offload tax, which means data transfer fee, how much you're using that, right? So that kind of things are available. So how to use VTune? VTune is part of the one API, so you don't have to, even though we are showing the module load one API, but you don't have to do that because that is already loaded by the default, right? So, and if you use a default VTune mode, deep VTune version, the current version is 25.0.1. It's a little bit old version than the latest one. Latest one is 25.2 version, I believe. So sometimes if we need some new feature or some bug fixes, we may have some newer VTune than the default one. In that case, you need to do the source, that specific VTune, and then you can use that. But during this hackathon, you don't have to do that. You can just use the default version, okay? And how to use VTune, just VTune and help and collect, and then it will show so many different collection mode. And then if you're interested in the specific analysis, for example, GPU hotspot analysis, you can do the VTune collect GPU hotspot, and then you can see a lot of the additional flag over there. Okay, I don't want to run this one. Okay, so this is pretty basic command line interface instruction. So one of the interesting collection mode is performance snapshot mode. This is different from application performance snapshot. It's kind of confusing, this different thing. So this is kind of the free analysis of your application. Okay, so if you do the VTune collect performance snapshot, it just try to check what kind of the features you may investigate after this step. So this is kind of the pre-analysis. So in this example, it says, oh, your code, based on this performance snapshot analysis, your code maybe get some benefit for some following up the hotspot analysis and threading analysis, HPC performance analysis, and something like that, right? So if you have some application running on GPU, and if you run the performance snapshot, I just tested a couple of days ago, it will probably give you, oh, you have pretty high the data transfer overhead. So because of that, you may need to use GPU offload analysis after this and something like that, right? So this is kind of the nice nice step to get some from hint which step you have to use after this one. So yep, and you can try it out. And APS, okay. So if you already ported your application on Intel GPU, and if you're confident about the device level performance or node level performance, you can directly go to APS analysis, which is application performance snapshot analysis. So left-hand side, you can see the HTML report. So it shows what is CPU time, GPU time, and the instruction per cycle, and what is CPU frequency, and then what is GPU utilization, vectorization, MPA time, etc. So if you see, so when you run your application with 120 node, and then you probably have some performance data, right? For example, some figure of metadata. So in my case, if I run some finite difference code and then 128 for each node, I got around 100 million cells per second I can solve, right? And then if I run 8 times more, for example, 1024 node, I can expect the figure of merit could be increased by 8 times, but somehow it didn't happen, right? So you'll be curious about why the slowdown happens, and then you may be curious about this is coming from the MPI or this is coming from some issues in the GPUs and etc. So in that case, you can use APS and the 120 node and 1024 node, and then you can see this data, GPU stack utilization and MPI analysis, MPA time. So if you see the longer MPA time between these two cases, you can see, oh, something happened in the MPI side. You need to look into the MPI part. Or if your GPU stack utilization has different data between these two cases, you may need to go into what is the difference between these two cases, something like that, right? So, APS provide it's compared to VTune, it's relatively lower overhead. So it is why you can run with a multiple node. So the running instruction is pretty simple. So like iProp for a unit trace, you can just include APS just after your MPI flag and before your application binary, okay? And APS and dash R, which means your result file names, and then your APS result directory. So you can just APS dash R and APS result, something like that. So, and then run it in the interactive jump mode or some batch jump mode, whatever you want. And then once you're done, you will see this APS result directory is created on your folder. And then in order to generate the report, you can just type on the login node, you can just type the APS-report and then that APS result directory, and then it generates HTML file like on the left-hand side, okay? And then you can see some overview data. And here, if you move around your tools, you see the tooltip is popping up and shows an MPI time and some variations. We will do it together later. So you can do that, and also you can also use the command line interface to see more data. For example, if you see here, MPI all reduced time is very high, for example, and you may be interested in, okay, which MPI rank has the highest MPI reduced time, or which MPI rank has the longest MPI wait time, etc. Right? So kind of some symptom of some memory MPI load imbalance issue, right? So if you're curious about that, you can use APS report and then some command line interface. I will show you later, and then you can see the how much times are used per MPI rank. So yeah, this is available. So from here you can see high MPI time. You can see high MPI time or GPU load GPU stack utilization or some physical core utilization, high memory store, etc. And then based on this data, you can go into the next step, which could be HPC performance analysis for the MPI activity and factorization, or some GPU analysis to understand if what happened in the GPU if you have some low GPU utilization. Okay, so this is one of two, and this one is from the VTune, so one of the VTune analysis feature called HPC performance characterization. So this is not just about GPU, but this is to see the overall performance on CPU and GPU, both of them. Okay, so even though you're using a lot of kernels on GPU, but sometimes your CPU kernel can be problematic, right? So in this case, you can run the HPC performance analysis. To run that, you can just use VTune and dash collect, and then HPC performance. So you're choosing VTune, and then inside the VTune, you want to use HPC performance analysis, and then dash R, and you'll collect the result file name here, okay? So if we run it, VTune will collect those corresponding the data per node level. So if you run with the multi-node case, for example, I don't recommend you to use VTune with 1000 node. Don't try that. But if you want to run or 2 or 4 node, if you can still try that, it's not recommended, but you can still try that. In that case, for example, if you run VTune with 4 node, you will have the 4 different result folder, because VTune will create different folder for the compute node. Okay, and then each compute node has the corresponding data there. Okay, so and then you can see some core utilization, vector engine utilization, or memory bound vectorization, or OpenMP region, or SQL compute task, etc. Right? So if you don't see what could be the main reason of the delay, you can start with HPC performance analysis. And then, but another analysis you can try is GPU offload analysis, which is to identify if your application is CPU bound or GPU bound, or what is the GPU the offload tax to use GPU, right? So you can see the allocation or host device data transfer, device host data transfer, and execution and synchronization, etc. Right? So this is, I can say, somewhat similar to what happened in the SI system on the NVIDIA GPU side. Not exactly, but somewhat similar. So as you can see here, it shows 60 different GPU here, right? And then it says, oh, this GPU has 2 stacks, and each stack spend some amount of time. So in this example, interesting thing is GPU stack 1 uses 93 milliseconds, and GPU stack 0 uses 33 milliseconds, which means that some load imbalance happened between these 2 stacks. I don't know what happened. And here you can see this color, the green color, is host to device transfer, which is pretty short, right? So we don't need to worry about that. And then yellow color is execution time. So in GPU 4, stack 1 has this amount of the GPU execution, and stack 0 has this amount of GPU execution. So in this case, okay, GPU utilization is It's pretty similar to each other. But what happened in the device to host transfer is stack one used this amount of time to complete the device host transfer, but the GPU stack zero has a shorter time than that, right? Something happened in this case. So because of that, the 60 millisecond difference between GPU stack 0 and 1 happened because of the device host transfer. And then now you find out, okay, you can check which part is transferring data from device to host, and then see what's going on this device 0 and stack 0 and stack 1, something like that, right? So this kind of information you can obtain from the GPU offload analysis. And then again here, with the Perpetual, VTune provides some nice GUI interface, so you can see at which time frame the GPU is active, or GPU is idle, or GPU is stored, something like that, right? So command line interface is pretty simple, so pretty similar to HPC performance analysis. So you can just add VTune dash collect and GPU offline and dash out and result directory name, and then you can just run it, right? Just run it, and then just be patient. So again, GPU VTune collect a lot of hardware counter data. So because of that, the overhead of the profiler is much higher than the other tools compared to iProf, Unitrace, some other tools, right? So you should put some sufficient additional time on your job. Otherwise, your job could be killed in the middle of the collection mode or the finalization mode. Okay, next analysis is GPU hotspot analysis. So if you are very confident about the CPU side, it should be okay. If you're confident about your CPU side of kernel and also GPU, CPU data transfer part, if you're very confident about those part, you can directly use the GPU hotspot analysis. So GPU hotspot analysis is providing some information what happened on GPU side. So you can see GPU kernel, each GPU kernel, how much GPU utilization happen, how much stall happen, how much idle happen. And also, it can provide which kernel has low occupancy or stalled, or which kernel has some. So you have a lot of GPU metric data for the kernel based. So you can see a lot of different. So L3 cache bandwidth, L1 cache bandwidth, or some X-Link bandwidth, etc. Right? So those kind of information could be available. Yeah, sorry, X-Link is available on GPU offload analysis, but other than the device side, whatever happened, you can see from the GPU hotspot analysis. So you can find out which kernel is hotspot, which kernel takes most of the time, which kernel has lower instruction count per cycle, etc. Right? So a lot of useful information available. To run that, you can do the VTune collect GPU hotspot. So now we are just changing the word after collect, right? So if you use the GPU hotspot after collect, you are using VTune GPU hotspot analysis. And then again, just be patient, put sufficient additional time to complete this collection. So after that, you can get some data. On GPU hotspot analysis, it has some different tabs on the GUI interface, and then you can also see the memory hierarchy diagram, which is pretty intuitive the representation. So here you can see, if you choose the memory hierarchy diagram, you can see some component of your GPU, right? So here you have the Xe cores. In the Xe core, you see the vector engines, and also the SLM, shared SLM, and the LSC, the L1 cache. And then between the Xe core to L3 cache, you can see how much the bandwidth happened between the Xe core and L3 cache. And from the L3 cache to HBM, you can see how much data transfer come in and come out between the L3 and HBM. And then PCIe and levels LLC is LLC, the last application on the CPU side, right? So this information happen, and this example, this is idle ratio is very, very high, 99%, which means you don't have enough work to populate all the GPU cores, or something's wrong, right? So yeah, it shouldn't happen in your application, right? So so as you can see here, you can see the data transfer bandwidth metric of total data movement or some read write bandwidth and also some percentage compared to theoretical peak, like that. And from here you can see, okay, there are a lot of transfer happen in L3, which means it could be pretty good L3 cache locality happen because you don't see similar bandwidth in between L3 and HBM, something like that, right? So yeah, there are meaningful data from here, and it's very intuitive. And also GPU hotspot analysis is some timeline view, like a GPU offload analysis more, but the more component. So here you can see 6 GPUs for different the categories, right? So you can see the GPU vector engine utilization and computing thread dispatch, XVE pipeline or instruction, or some GPU BG or the frequency or S3 cache bandwidth, etc. Right? So this is just the next step of the memory hierarchy diagram. So if you choose a platform, you can see what is GPU activity going on. So yeah, here. So if you don't choose any specific GPU, you will always see the all different GPU together, and then you can choose what happened in GPU 0, GPU 1, and GPU 2, but kernel based. Okay, and then up to now, we were talking about the kernel-based analysis, which means uh, you don't need to build your application again. So whatever optimization, any optimization level is okay. You don't have any debug symbol required. Okay, so you can just run it without rebuilding your application, and then VTune will provide, and VTune and APS will provide which kernel which kernel spend most of the time and which kernel has how much metrics, how much bandwidth to use, something like that, right? So, but some cases, your kernel can be pretty big, right? So I heard that some kernel could be hundreds lines of code, or maybe more than 1,000 lines of code. So in that case, you already know that kernel is hot kernel because that kernel do the most of the work, right? So in that situation, kernel level analysis mean nothing because you already know this kernel is hard kernel and it is doing everything. You want to know which line of this kernel spend how much instruction, how much time, how much latency have something. That kind of information you may want to have, right? So if you want to do that, you can try the source level in kernel profiling analysis. So in this example, you have to build your application again because in order to see your source line, you have to provide some symbols to the profiler. For that, you can build your application with the -f debug info for profiling and -g line table only. These two compiler flag is required. And once you build your application with these two flags, VTune can provide source level in kernel profiling data. So this example is dynamic instruction count data, which means how many instructions executed per line based. So, and then what types of the instructions are executed, right? So, to run that, you can just do the VTune collect GPU hotspot analysis and then add additional knob for the instruction count here. So knob characterization dash mode is equal to instruction count, and then dash out with different folder name, and VTune will generate this kind of data. So and then you can open up some specific the files. So in this example, ISO 3D FDF a DFD kernel, and then once you open it up, it shows okay, so this line of kernel provide 97 million standard instruction and 39 million no 390 million the single precision instruction and the double precision instruction, etc. Right? So you can see that. So this is useful. Sometimes compilers are great, but sometimes compiler generate the assembly not optimally in some cases, right? So yeah, that is one way to use instruction count. So if you, for example, you expected in this line, you just expected some FMA instruction mainly, but if you see a lot of the integer operations or a lot of some control flow instruction happen, that means compiler did something wrong, right? Not wrong, but something not optimal, suboptimal code generation happened, right? So this kind of information you can check with this instruction, and also maybe some minor code typo or mistake, you can also catch that. So This is one way to check the instruction count analysis. Another thing is the just counting GPU cycle, right? So more instruction means that line can take more time, but it may not be true all the time, right? So number of instruction and number of cycle could be very, very different, right? So if you want to see how much cycles are used per line, you can use basic block latency analysis. So again, your code should be built with this additional info. And then what you need to do is you just need to replace your knob. Instead of instruction count knob, you can just use a source analysis knob here, okay? So if you use this additional flag after VTune GPU hotspot analysis, your VTune will provide this cycle data. And then in this case, it just count every cycle and then provide, okay, this line of your code span this much of cycles. So now this is, you can consider this is kind of the word time thing, right? So more cycle means takes more. And also instruction count analysis, if you have some stall happen because of the memory dependency, the instruction count still shows one instruction, but in the cycle, because of stall or the cache miss or etc., it will also include some count, some cycle because of that impact, right? So it's kind of the different feature and different purpose. Okay, so this one is also available. And the memory latency analysis, if you have some memory activity and if you think high memory stall or etc., yeah, you can try the memory latency analysis and see whether you are using kind of expected latency or higher latency or not, right? So that is also available. So for that, you can replace this additional knob. Okay, you can use source analysis, and then you need to add additional source knob here for the memory latency analysis. Okay, so Eric added some comments on not having much success with APS or VTune. When I try to use APS on NAMD, I get the sort of error, parse and APS error while loading share library. So cannot share the object files, such file. Okay, so it looks like APS doesn't recognize the specific library, so we need to use LD preload or accept some additional environment variable we need to set before running the APS. So so maybe Eric, after this talk, we may try together to resolve that issue. Okay. So again, yeah, as Eric mentioned in the channel, so with the real application is different dependency on different shared library or different code paths, right? So because of that, sometimes tools can be sensitive to some specific situations. So if something happens, just let us know so we can dig into together to resolve the issue. Okay. Okay. So back to the slide. Memory latency analysis is useful to see how much time cycles are used for the memory read and write. And another interesting feature is hardware-assisted store sampling analysis. So most of the time, what happens is even with the same number of instructions, you may take a lot of cycles per specific node. That could be because of some stall happen. And without some additional knob, you'll be told, oh, stall happened, and then what? What can I do? So in order to do that, in order to find out what is your next step, you have to know, you probably want to know what types of stall happen, right? So Intel has this hardware assisted stall sampling analysis. So using this additional knobs, so now knobs become longer and longer, right? So just use this one as your cheat sheet. So using that, you can. So here in this example from the instruction count analysis, you see, no, this is a memory latency analysis, I think. Oh no, this is sampling analysis. So once you do that, it has the 42% of stall happen here, right? And then if you run that, you can see additional the data from stall count data, right? Using that analysis. So you can see, oh, stall happen, and your active ratio is here. So your stall happen because of control instruction is 0.1% is negligible. Okay, that's okay. And pipe, which means stored due to the data hardware, the structure hardware, or reasonable resource unavailable is this one. So send instruction, and this is delayed in the distributing of the instruction to the XPE, and this is stalled because of the dependency tracked by the scoreboard mechanism, for example, data hard or something like that, right? So this kind of additional data you can find out, and you may be able to find out what could be the next step to tackle, right? So this is also available in VTune. And sometimes you may be interested in, so you may have some nice the API communicator. So some communicators happen inside of node, and then another communicator working on the intranode, etc. Right? So in that case, you may be interested in if you're utilizing Xlink well or not, right? So or you may be interested in your Xlink usage is your performance value or not. So in order to understand that information, you can run the GPU offload analysis with additional knob to analyze Xlink usage is equal to true. With this knob, VTune will generate some we will collect the hardware data from the Xlink, which is GPU to GPU link, like NVLink type things on the media side. So, and then you can see this kind of visualized data, how much data transfer happen, what is bandwidth, etc. Right. So this is also another type of analysis. Okay, and 1CCL, we see a lot of demand for the 1CCL data because many machine learning application users are using 1CCL and they want to know what happened. So for that, 1CCL APS also provides some time spent on 1CCL and also some percentage of time. And also, if you do the HPC performance characterization analysis, you can see 1CCL time and the top 1CCL task and some communication task in the summary window and timeline. One has always this feature is implemented recently, so you may see a lot of issues. So actually, we have our data science colleagues are using this 1CCL on the APS and VTune. They also realize some issues. So if you see that, don't hesitate to reach out to us. We have we are collaborating with the VTune developer pretty closely, so we wanna bring more issues and report those issues to them. So this 1CCL feature will be matured pretty quickly. Okay, but what I want to say is, if you are interested in the CCL data, there are two options: using APS and HPC performance analysis. Okay, so I just this is kind of end of finishing the overview of the VTune analysis, and then one thing you need to keep in mind is VTune collects a lot of data, and VTune has a lot of different features, and each feature has require a lot of data collection. Because of that, collection overhead is not it's pretty significant. Okay, so depending on the application and depending on which feature you are using, but you should be very, very patient about finishing your collection. So next question is, what can you do if we want to reduce that overhead? Okay, so this is a list of the items the Intel recommended us to try it out. Okay, so first one is if you are just working on the GPU side, maybe you may disable the stack collection on CPU side, right? So if you add the knob enable stack collection is equal to false, that means you minimize the stack collection on the CPU side, and you may see lower overhead than without them. And also another thing is the modifying sampling interval. So right now the default sampling interval on GPU is 1 microsecond. And if you see your kernel execution time is in average longer than that interval, you may increase the sampling interval to the 10 milliseconds. That means your hardware counter data, amount of hardware counter data is 1/10 of the default one. So that means you will have a smaller data set and shorter overhead, right? But is pros and cons, right? So if you have so many different kernels and every has very short runtime, you cannot reduce that. If you reduce that, you still see some data, but the accuracy of those data is not good, right? So it is a pros and cons, so we can use that. And also, by the default, VTune collect the performance data of the every GPU kernels. So that means if you specify some kernel of interest instead of collecting everything, you can also reduce the profiling overhead, right? For example, compared to NVIDIA side, NVIDIA NCU, NVIDIA Inside Compute, the default setup is collecting a specific kernel data, not collecting every kernel data, right? So, but the VTune has different approach. It's kind of the top-down approach, so it collect everything. And if user specifies some specific kernel of interest, they can just collect that specific kernel. So, using this knob computing task of interest, and then so you can use a wildcard and some kernel name, and you can just collect that specific kernel data instead of collecting everything. So in this way, you can also minimize some overhead, right? So there are more details in here. If you click there, you can see more options here, how to minimize collection overhead. So you can also look into this material, okay? Okay, so this is one way. And okay, another thing is now default mode is VTune collect the data from the old MPA rank, which means if you run the 12 MPA rank on a node, VTune will collect the 12 MPA rank data, right? You may see your application, each MPA rank runs similar workload. In that case, you don't have to collect all the MPA rank data, right? So if that is true on your end, you may just select one of MPA rank instead of everything using npmd mode. So in this example, like I showed you in unit trace case, you just attach this VTune to the first MPA rank. So MPA XAC MP1, right? And then VTune that's the GPU hotspot, right? And put all the command line interface, and then put the colon and dash n 23, which is remaining 23. I don't attach the VTune to those MPA rank, just run without VTune, right? So if you use this npmd mode, you are attaching VTune to specific MPA rank, and then VTune will collect performance data for that specific MPA rank. So this is another way to reduce the some overhead, collection overhead, also finalization overhead. Okay, so this is kind of example of hack application. So in hack application, they smartly use this kind of a shell script. So they have some selected rank for the profiling, and then using the if statement, if the pmix rank is in the selected NPL rank, they use this VTune command line. Otherwise, they just use the general command line. So you can also modify this shell script for your application. Okay, so this is kind of very naive comparison what happened with hack. So in a single node and four node case, application word time is 36 seconds. And if they collect only one MPA rank, it takes 47 seconds, which is pretty small overhead happen compared to 36 seconds, right? But when they profiled all the MPA rank, it took around 5 minutes, including collection overhead. So in this case, it's very significant, right? So definitely in this case, just use a single MPA rank instead of the rank all the GPU or the MPI from the four different nodes, right? So this is good example. Storage overhead wide, still see some difference profiling one MPI rank versus all MPI rank, but it's not very significant because VTune is collecting the hardware counter data from all the GPUs, even not used by the MPI rank, right? Because of that, the storage side overhead is not big difference, but there's another way to reduce that as well. So yeah, this is some kind of Rupak did some small study to show how effective this approach is, and then to me it looks pretty effective. Okay, and also, okay, so previous one is without finalization, and the second one is including finalization. So if you include finalization, the difference become also pretty big, 3 minutes versus 7 minutes, and 1 GB versus 2.6 GB for these test cases, right? So this is some study, and another thing is you can also add additional flag to specify uh, the GPU you want to monitor. Okay, so by the default, VTune monitored all the GPU performance data. But if you add this knob target GPU and the PC address, VTune just look at that specific GPU, not others. So in this case, you can also reduce some collection overhead, right? So MPI, selective MPI profiling and GPU target GPU knobs. If you use both of them, you can reduce the overhead pretty well. Okay. So again, I know just watching this slide may not you 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 may be confused. So if you are concerning about some overhead and if you want to use either of them, please reach out to us so we can help you out. Okay. Okay, so this is comparison between using the GPU, target GPU one and without that data. And also you may disable some API collection. So using some collect from API force, you disable the even core stack on GPU side. So if you have very significant overhead, you may consider to use that. Okay. Okay, so before moving on ITT API, maybe any question? Okay. Maybe you're too tired to listen to additional profilers. So anyway, I think this is recorded, so maybe once you get some new energy, you may see again. It's up to you. But anyway, okay, let me move on. The next one is ITT API. This is specify which area of code you want to collect the performance data. Okay, so this require your source change. So this is not very convenient to use, but once you include that, you can manage your the collection overhead pretty well. So this is not just kernel level. You can also collect some part of kernel, etc. Right? So this is available for C++ functional environment, and you can use this additional instruction, use LD library pass and then just run it, right? And this is kind of the example. So ITT task begin, and then you have some work and ITT task end. So if you run it with this ITT API, VTune will just collect the data for this selected part. And that is also available on the Python, the API. So PyITT API is available. So if you're working on the machine learning workload, you can also use same concept but different syntax with the PyITT API. So this is example of the PyITT API. So yeah, you can use this case. This is kind of PyTorch example, I think, and then um, they are instead of using the start end, they're using the range push and pop and mark, etc. here, right? So torch profile ITT range push and then torch profile ITT range pop. So you can use the syntax for that. And then next one, okay, I almost finished the VTune part. So, and then this part is useful to use the GUI interface of VTune. So as you can see, VTune provide a lot of different GUI information, GUI representation of data, some hierarchical view or some timeline view. This is very useful. But in order to use them, you have to enable the GUI interface, right? So X11 GUI interface is not very convenient because it has a lot of latency between the Aurora and your local system, right? So using X11 is too painful. We have some kind of another PNC type approach, but yeah, that's not available yet. So VTune provides some another approach to use that called VTune web server type approach, which means uh, it's pretty lightweight and also very minimal latency we see, right? So how you can use is first of all, so let me come back to step one later, okay? So first of all, what you need to do is you need to SSH to your login node and then, right? And then module load one API, which is already loaded, and then run the VTune backend, and the data directory is equal to some location you already have for the VTune collection data. So if you run it, it will show you some the IP address with some port number. So you need to grab that port number and then open new terminal with SSH forwarding using this syntax. And once you establish that, you can copy and paste the IP address and port number on the Firefox web browser. And then you can see, you can use that Firefox web browser as a VTune GUI interface. So, it is not really good representation. So I will show you how to do that, okay? So one requirement for this execution is once you run the VTune backend, you have to use the same login node for the SSH port forwarding. So what happened is VTune at the Aurora has a different login node, right? So once you run the VTune backend, for example, login 9, you run the VTune backend. And then if you do the SSH-L, you may grab the login 9, or probably you would have another login node, right? So login 10, 11, 12. If that happens, this SSH forwarding is not established between the VTune backend, right? So in order to avoid that situation, what you're recommending is on your local laptop, you have a .ssh config file. So in this file, please add these 3 lines. So if you add these 3 lines, whenever you access to the ALCF system, Polaris and Aurora system, what happens is it just save your login credential, and then we use that and grab the same login node. Okay, so if you have these 3 lines on your .ssh and config file, you don't have to worry about, after running VTune backend, you don't have to worry about getting some other login node with SSH-L. Okay, so let me show you how to do that here. Okay, so what you need to do is I have a login node here, right? So let's say, oops, I think I lost Aurora. While I'm establishing the access, please speak up if you have any question. Okay, while we are waiting, let me go over a little bit more, okay? Okay, so I will show you how to use VTune backend for the GUI, and while I'm waiting get to Aurora again, let me move on, okay? So this is the last slide of VTune, so it just have all this is a cheat sheet, so you can see what kind of command line you can use for the GPU offload analysis, hotspot analysis, and the instruction count analysis, etc. Right? So you may use this slide for your tip slide. Okay, so I just lost that. Okay, so I lost that. Let me just open up my SSH and config file. Okay, so here I have these 3 lines, right? Host and asterisk and acf.gov and the control master auto and control path SSH, SSH mux, MUX and HNP and R, right? So since I have this one, what happens is if I just log into the Aurora, I have to type my credential here. So let me log in to here. Okay, now I grab the login 12, right? And then on next terminal, if I do the SSH again, I don't need to type my credential again, and then I get the same login node, 12 node, right? So this is pretty convenient. And it's required for the VTune backend, right? So in order to run the VTune backend, in my case, I have example here, right? So VTune backend, so module list. I already have one API, 25.0.0 here, right? So I already have VTune backend, and dash data directory is equal to, I would like to use this folder, so tools and Intel folder in the future. So if I run it, you see some statement happen, and then it shows VTune Profiler GUI is accessible through the HTTPS 127.0.1:40577. This is dedicated to me. So while you keep this terminal, what you need to do is I will connect SSH again from my local machine here. So I will copy from 1 to 7 to this port number. And instead of -y, I will just use -l, copy paste, colon, copy paste twice. I don't know why, but we have to do that. So SSH-L and copy pasted the IP address and the port number and colon and copy paste again. And then I just log into the login node. Okay, now it's established, right? So I run VTune backend on the login 12, and then I just established SSH port forwarding to the login 12, right? So nothing happened, but you're ready to use VTune backend server. So now I copy from HTTPS to the end, and then let me open the Firefox. Just use Firefox for this one. Other browser is too much, it has a higher security requirements, so doesn't work. Okay, so I just copy and pasted this HTTP and IP address and port number. So I'm warned. So potential security ahead, I will choose advanced, and then accept the risk and continue. So if you do that at the first time, you will see this consent. And then you see this VTune GUI interface, right? So now you can use that. So this is how to use that. So yeah, please try it out and let me know if you have any issue, so we can help you out. Okay. Okay, so that is VTune backend server establishment, and then next part is Intel Advisor. Let me quickly go over that. So we don't have much material. So Advisor is another tool different from VTune, but different approach. So as you can see, VTune has a lot of so many different features. I would say this is a kind of progressive profiling approach. So once you run the APS, you have you may have some clue from the data analysis, right? So from that analysis or identifying bottleneck, you may want to go the next step, possibly HPC performance analysis, offload analysis, or GPU hotspot analysis, right? So you go there and do the kernel analysis, and then you find out some hierarchical diagram and see what is the cache bandwidth, and then you may see, oh, maybe this kernel has a lot of overhead, so I want to see what is instruction counts, and you move on that instruction count. So you have every part, you need to identify what's going on, and then think about what could be the next step and next step, right? So that is the VTune approach, some progressive approach, but Advisor is somewhat different. So Advisor has some pre-selected the metrics of interest, and you just run the Advisor, and then the Advisor just collect all required data and process that and provide some tips. It is why they call Advisor. So one of the popular features of Advisor is roofline performance analysis here. So, and also vector optimization and other types, but I'm going to talk about roofline analysis here. So Roofline analysis is basically you categorize your kernel in terms of the arithmetic intensity and the plop count, plop rate. So on x-axis, so at every kernel, advisor collect the number of plops and number of data transfer on the different cache hierarchy. So, and based on that, it compute what is the arithmetic intensity of that specific kernel. Okay, so that just find out what is your x-axis in this loop. Then y-axis is how much time spent and how much plops used for the double precision, single precision, etc. So it shows that determines what your y direction. And then it has some actually roofline, which means you cannot go beyond that because that is kind of the speed of lighting concept, right? So you cannot get the more bandwidth than the specification, right? So this is kind of your the best performance you can get, right? So here you can see multiple kernels here, and then they have some corresponding the x data and y data. And compared to here, F is very close to this inclined loop, and then G is away from the inclined loop. You can say F has a higher efficiency than the G because it has the smaller headrooms compared to the G, right? So this is kind of Rupak approach, very simple description. And this is the instruction on how to use that. So it's just one API is already loaded, and then just specify which vector you want to use for collection. So we call it PRJ. So you can just change the different name. And if you don't use MPI, you can use the wrapper, roofline wrapper. So roofline collection mode execute the required the collection together. But if you're using MPI, you have to use the two different steps. One is the survey analysis, and the another is the trip count analysis, right? So for the same executable and same input. So you run twice with these two options. And once you're done, you just generate the report, HTML report, and then you can see the data. So this is kind of the screenshot of the GPU roofline, the HTML files. So on left-hand side, you can see the roofline. So this is HBM bandwidth, S3 cache bandwidth, and SLM bandwidth. And this is double precision vector FMA, single precision vector FMA, and the double precision, single precision, the add peak and add peak or merge peak, right? So you have this kind of data, and then you can see how much data traffic happened, what is your arithmetic intensity per kernel based, right? And see some memory metrics or some instruction count and etc. So this is kind of a quick overview of the advisor. So let me give you some demo for these features, okay? Okay, so let me go back to, I have this one. So let me grab uh, on a note. Times dash A GPU hack dash Q GPU hack. Okay, so let me grab the one note for the practice. While we are waiting, let me go to my folder here. So, okay. So if you go to that folder, exam folder here, so Rooster, Flare, Project, GPU hack, and example, and tools, Intel. If you go there, you can see the REF file here. And I just put the pre-collected advisor HTML file and then an APS the report file here. Okay. So while I'm waiting, oh, I got the node, which is great. So the interface. So we already built the example from the previous lightweight tool. Let me skip that. And for APS one, it's very simple. So just use the APS and APS result here, right? So what I need to do is MPI run dash N12, GPU tile compact, and APS, dash all, I will say APS result, and comp, okay. So if you just run it, again, this is very quick benchmarks. It doesn't take a lot of time. Sometimes you may see warning. Don't worry about that. Okay, it's pretty quick, and then it's quicker than expected. I don't know if it was successful or not, but it says just do the APS report and result here, right? So let's do that. Oh, so once you do that, you see, okay, this is application name, number of rank, number of number of rank per node, and this is elapsed time. This is kind of all text-based one, right? So let me grab this file, 15. Let me grab this one. Okay. Problem is, I just get the two file and probably this one. Yeah, this one just executed right now, right? So yeah, once you get the HTML file, you see, so previously on the command line, you see all the data in the text, and the same data is showing up in here, okay? So if you move your mouse, you can see some tooltip is popping up, and some additional data and what it means. You can see that, right? So here, MPA time, you can see 61% used, and then you can also see the ratio, I mean, the bell curve of this one. So 58% to 62.75%, etc., right? And also GPU active ratio 75%, store ratio is 20%. And yeah, this is kind of the bean chart of the MPI init, reduce, finalization, come, right? So this is kind of a quick overview from the HTML file. It does not provide a lot of GUI interface, but this is kind of good to see at the first glance. But this is not all the data you can see. So actually, you can see more data from the collected data here, right? So here you have APS result data, and what you can do is you can check what kind of metrics are collected from the APS results. So what you can do is APS report, and then dash metric and question mark, and then your APS result data here. So if you do that, what it says was, okay, in this collection, APS is collected this kind of data. So MPI time, MPI hotspot, disk IO, virtual memory usage, memory store, DRAM bandwidth, or GPU, inbound, outbound, PCIe read, XB state, etc. Right? So if you wanna see more data, what you can do is you can choose some of them. So this is example, APS result. So what I'm doing is APS report, and that's just metrics, and start quotation mark, and GPU stack utilization, for example, stack utilization for the device. I will add that. And then this is OpenMP application. Let's use OpenMP offload time, and maybe GPU accumulate time per device. I want to see because I'm interested in if load imbalance happen or not. And then let's see MPI time, okay? MPI time, and then APS result. Typo. APS report. APS result. Maybe okay, yeah. So once you run that, what it shows was it shows a node name and the rank name, and what kind of metrics are showing here. So MPI time of rank 3 is 0.8 second, and the rank 3 is 0.8 second. Okay, it's pretty good. And OpenMP offload time is pretty similar, so 26 millisecond across, right? Around 20 to 26 millisecond. Okay, it's pretty good. And GPU accumulation time per device is also very short but pretty equivalent. So I don't see any load on load imbalance, right? And stack utilization is pretty low because it's simple benchmarks. With your application, you will see much higher than that. So this kind of data you can also collect in addition to the HTML file. So this is a quick demo of APS analysis, and let me run the GPU hotspot analysis for the example. Okay, so what I did was so I ran this one for the APS analysis, right? So for the VTune GPU hotspot analysis, you can just replace VTune, collect hotspot, and dash all, and let's say VTune result, okay? And the GPU 8 hotspot GH. So if you do that, you will start collection, but it will take a little bit longer time than usual. I mean, compared to APS collection, because APS is relatively lightweight compared to VTune. So let's just let it run, okay? So while we are waiting, yeah, it just execution is done, but now collection and the post-processing takes us some time, so we should have some additional time. So it says collection stopped, and then it's kind of the finalizing the data, right? So while we are waiting, for advisor, you can use this example. I'm not sure I can run it this now, but uh, the instruction is the same, right? So I just attach advisor to the first MPI rank. So MPI XDC-N GPU type compact advisor collect survey profile GPU project directory. And then using npmd mode, the remaining 11 MPI rank I'm running without the advisor. So first line is survey analysis. The second line, you have to run it after once you're done. The survey analysis, you need to run it again with the three-quarter analysis. So once you complete these two collection, you need to generate the report file with advisor dash dash report all project directory, and then like this one. So once you do that, you can just download this loopline.html file. So while we are waiting, if you go to the audio file, you can also see this example. Okay, so oh, this is AMRB example. So APS case, I ran it with 16 nodes, so you can see compared to the previous one, it's pretty different, right? So here the MPI and yeah, this word time, idle, active ratio. This is the APS result, and you can also open up the advisor report here. So if you open up the advisor HTML file, you can see this view. So this is a summary view and it's showing GPU line and CPU line and what is your hot kernel. So this is MNX kernel, so it has different MNX kernels spanning different number of time and GPLOPs and in the integer operation, etc. Right? So, and if you want to see more details on GPU loop line analysis here, you can click the GPU regions. So this is a real application. There are so many different the kernels here, right? So, and by the default, advisor collect corresponding data, not for the kernel invocation, but for the kernel. So you can see here some corners are green dot, green color, some corner is a yellow dot, and some corner is a red dot. Red dot means it takes more than 20% of time. Yellow is between 3% to 20%, I think, and also the green is less than 3% or 1%, yeah, something like that. So here you can see, oh, this one is problematic. So you can see click, right? And then you see the plus sign here. If you click the plus sign, it will just show additional corner here. So what I mean is this red one has the same kernel name, but even for the same kernel, they may have some different the group size, right? So depending on the group size, performance characteristic of the kernel could be different. So it is kind of aggregating the data, and then if you click the plus sign, it shows all the subgroups of these kernels, right? So depending on the work group size here. And here, same thing happened here. So this is saying collected from the GPU adapter 0, and then the elapsed time, and the plot count, integer operation count, and you see the work group size is different, right? So this work group size, this work group size, and then if you extend this to triangular shape, you see some detailed data per work group size, work size, right? So this one, and then you can also see the kernel time, and this is CARM, the memory traffic, so total memory traffic, L1 traffic, read write, SLM, and L3 traffic, memory traffics, right? So if you extend the specific column, you can also see additional data here. And it also checks the register speed. So if you're curious if your kernel has register speed or not, you can also use advisor and XPE array. So for example, even for the same kernel, for the big work group size, you see 78% of the active XPE ratio. But for the same kernel, if work size is small, for the same kernel, you may see the idle ratio is really high, 99%, right? So, and also the occupancy or some IPP or EM instruction, IPU instruction, vector range instruction, etc. So this kind of data are provided by advisor in the one step, I mean, one execution. So again, this is difference between the approach on VTune and advisor. VTune provide a lot of additional knobs. Advisor collect pre-collected, pre-configured data and provide some performance tip based on that measurement, right? So yeah, this is kind of a quick overview of the advisor. And if you choose different kernel here, the GPU details keep changing, right? So you can play around for your hot kernel using the analysis. So okay, this is completed here now, right? So you see the VTune result, GH, and then the login node number here. So we established VTune backend server here, so we can go back to the Firefox and just refresh. Hello. We'll see. Uh, Interesting, it should show up somewhere. Uh, Interesting. So it doesn't show up. Let me see what happens. So let me disconnect that. And PWD home. Let's choose my home folder instead of that folder. Okay, so I need to reestablish SSH back forwarding again. So here, okay, once it's done, I copy this HTTP file here, paste again. Advance, and accept risk and continue. Okay, now on the left-hand side, I see multiple folder here, right? So tools, Intel, I will just expand it and then see the VTune result dash GH. So if I double click that, in this VTune web server mode, just bring the data from the Aurora to your local system. Compared to X11, the latency is much smaller. So, but still, loading time, you can give it some loading time here. Okay, so yeah, so now it's loading here. So it is summary view, right? Okay, now it says 6 GPUs are available. This is the HPC benchmark, the quick benchmark. So either it's very high, but don't worry about that. And then the different stacks. And then if you go to graphics here, you can see it's loading. Yep. You can see the 6 different GPUs, right? And then you see the hierarchical view here. So Xe core traffics between the Xe core to L3 and L3 to HBM. And you can expand the GPUs here. So I have a GPU 3 and stack 0, and then you can see multiple the kernels. So in this benchmark, I just have one kernel, so I just click this one kernel. So this hierarchical the hierarchy diagram is updated for this specific kernels of interest I chose, right? And then you can go to platform here, and you can expect some timeline view here. It's coming popping up. So we are running same problem as the unit trace case and the iProp case. Unit trace and iProp use a perpetual and it use its own GUI interface. So we can zoom in using the GUI here, right? So popping up again, right? So here, so at this time point, you have OMP, the G event host synchronization happen. And then if you go to here, you can say, this is a comp geo OMP offloading 20, line 29, right? And then you can see here, you see, okay, this is the ALU 0 and 1 utilization, XP, send pipeline, branch pipeline, etc. So you can move around and see what happened here. So yeah, so this is how to use the VTune. And again, you can use same VTune backend mode for the other VTune analysis, the GPU offload analysis, HPC performance analysis, or source line in kernel analysis. Everything you can use the same VTune backend mode. Okay, so I think that's all I have. And we have 7 minutes. I know this is a long day. You need to here listen to many different tools today, but this is all for today. Any question?
Thank you, JaeHyuk. Are there any questions for JaeHyuk?
Hi, Jacob. This is Marta. Can we get cache misses in any of the tools that you show?
Cache misses. I think probably between cache misses. Cache bandwidth we have, but I'm not sure about cache misses. Yeah, I think VTune also process raw data to visualize some specific information, right? So I don't think VTune shows cache miss data directly. Let me see. So Bit Advisor also does not, because cache miss data is raw counter data, right? So it doesn't show that, but you can get that information using the advisor feature. For example, let's look into this one, okay? So let me select only this one. And then if I collect here on the float, I will choose different memory hierarchy, memory levels here, right? So if I apply that, you can see that is the memory traffic for the COM, L3, and HBM here, right? So from here, what you can see is cache miss is basically you don't let's say if you have a lot of L3 cache miss, that means you don't have good enough L3 cache locality. Because of that, you cannot find out that data on your L3 cache. So you have to go to HBM, right? Which means L3 cache traffic and HBM traffic could be somewhat similar because you have a lot of L3 cache miss, right? So from this data, it says the L3 traffic is 500 gigabyte and HBM data is 120 gigabyte, which means it is pretty good cache locality, right? So just the access ratio is 1 to 4 to the L3 and HBM, right? So that is how we, analyze those data. But if you want to get the L3 cache miss data or cache hit data directly, I think you can use the unit trace data, PTI GPU. So we trace. Oh, this is okay, sorry. So unit trace data, unit trace is more like grab the raw hardware counter data directly from the counter data, right? So here, you can use you can choose the sum of metrics from cache misses. So here it is the number of L3 caches which is missing in L3 cache, something like that, right? So if you wanna get that specific raw data directly, I think you can use the unit trace tool. Or if you want some process data to get some performance hint, I think advisor or VTune is still a good tool for that. Does it make sense?
Yeah, thank you so much.
Yep.
Sorry to interrupt. I still have a question. What's the definition of cache miss? Basically, the data was not in L3 and had to be reloaded, or missed in the sense that.
So whenever your kernel execute some instruction, right, that requires some data for the instruction, some data in the dependency, right? So probably your register try to bring that data from some level of your cache hierarchy, right? So if that data exists on the L1 cache, you can bring the data from L1, right, directly, and then you don't have to worry about what happened in L3 and HBM, right? But somehow your L1 cache does not have that specific data. Your L1 cache will say, oh, L1 doesn't have that data. You have to go to the higher level of cache, L3. That means L1 cache miss happen, right? And then your XP engine will go to will request the data from L3 cache. And if data is exists on L3 cache, that means L3 cache hit happen. But it still doesn't exist, and then you have to go to HBM. That means L3 cache miss happen at that event. So that is kind of very low level instruction level operations. Usually you don't need to worry about it too much, but yeah, that is the definition. I don't know. I'm giving you the correct the proper answer or not.
Thanks.
Sure. So yeah, I don't feel very happy to provide too many different tools because more tools doesn't mean better, but at least better than nothing, right? So I understand there are many different tools. Yeah, believe it or not, I don't introduce every tools. I just introduce some selected tools. So, but what I can say is some tools have some similarities. Some tools have very different features. So there is no one, super tool to provide your performance hint correctly. Unfortunately, it's not true yet. Maybe someday AI ops is available. Maybe you can get that, but not yet. So my recommendation is to just start from some. I mean, you need to identify what you wanna get, right? So you cannot just say, oh, my application performed very bad. What can I do? In that case, the answer could be very wide. But if you say, oh, if I do some weak scaling study and then I see with a specific number of nodes, I see some efficiency drop very quickly. So that could be a little bit more specific, right? So and then you can start with APS. And you may say, oh, when I run this input file and then GPU, I mean, I think the form data is pretty good, but when I run another input part, possibly using some different types of kernel or different configuration. In that case, I see the form data drop very quickly. So for that case, it's very obvious. Oh, something happened in the GPU kernel level issue or some different ratio between the kernel execution, right? So in that case, VTune GPU hotspot analysis could be beneficial. So if you want to use some performance tools, first of all, think about what you want to get, what is the symptom, and what you want to tackle, right? So if you define your problem well, that means we can find out appropriate tool for tackling, I mean, resolve that issues, okay? So I know that's not a good answer, maybe more confusing you, but that's what we have now. And this is not only on Intel, even on NVIDIA side, I experienced the similar things, right? So yeah, I hope it is helpful to you. And again, this is just intro. On the in-person week, you will investigate a lot of different issues. So if you need any help, please feel free to let me know so we can bring the appropriate expert to you. Okay.